subgroup. So do you remember what was a subgroup?
Yes, ma'am. It is a subset of a group with the closure property and inverse.
We can simply say that a non-empty subset of a group G, which is itself a group under the operations of G.
Yes.
A non-empty subset H of G is said to be a subgroup of G if it is itself a group under the operations of G. And it is denoted by next is proper subgroup. A subgroup H of G is a proper subgroup of G if H is not equal to G, and it is denoted by this. This equality will be removed in case of proper subgroup. Next, trivial subgroup. Identity element and group G itself are trivial subgroups of G. Note, Zn is not a subgroup of Z. Next, we will study subgroup test. There were two types of subgroup test, one step and two step. One step subgroup test. Let H be a non-empty subset of a group G, then H is a subgroup of G if for every A comma B belongs to H, A B inverse belongs to H. Means I am taking two elements from this subgroup H, and if AB inverse belongs to H, then H is a subgroup of G. Second, two-step subgroup test. Let H be a non-empty subset of a group G, then H is a subgroup of G if for every A comma B belongs to H, AB belongs to H, and for every A belongs to H, A inverse belongs to H. The definition which we were telling in the starting, this is closure and this is inverse belongs to H. Next, finite subgroup test. Let G be a finite group a non-empty subset H of G is a subgroup of G if for every A comma B belongs to H, AB belongs to H. Let us discuss some examples of subgroups. First, nz with respect to plus operation is a subgroup of integers with plus operation for each n belongs to natural numbers. Second, z with respect to plus is a subgroup of q with respect to plus. So I can say that nz with respect to plus is a subgroup of z plus. It is a subgroup of rationals with respect to plus operation. Rationals are subgroup of real numbers with respect to plus operation. Real numbers are subgroup of complex numbers. And similarly, non-zero rational numbers with respect to multiplication operation is a subgroup of non-zero real numbers with respect to multiplication operation. One comma minus one. This is a subgroup of 1 minus 1 iota minus iota. If n divides m, then mz with respect to plus operation is a subgroup of nz with respect to plus operation. SLNR, this is a subgroup of GLNR. GL is general linear group. In which determinant of matrix is non-zero, and SL, this is special linear group. In this, determinant of matrices is 1. Next, Some important subgroups. First, center of a group. Let G be a group. The center of the group denoted by ZG is the set G belongs to group G such that Gx is equals to Xg for all X belongs to G. It is like commutative property only. So, if our group G is abelian, then I can say that center of group is equals to group only. Also, center of group is a subgroup of group G. Second, centralizer of an element of group G. Let G be a group and A belongs to G. The centralizer of A in G is the set CA. This is equal to G belongs to G such that AG is equals to GA. CA is equals to CA inverse. If I take A instead of A inverse, then I will get A inverse G is equals to GA inverse. And if I pre-multiply by A and post-multiply by A, then I will get GA is equals to AG. That's why CA is equals to CA inverse. Also, center of group is contained in centralizer of A. So, center of group is intersection of centralizer of A. And if G is abelian, if and only if G is equals to centralizer of A. Also, centralizer of A is a subgroup of G. Third is centralizer of a subgroup. Let G be a group and H be a subgroup of G. The centralizer of H in G is the set CH is equals to G belongs to G such that GH is equals to HG for all H belongs to H. Centralizer of H is a subgroup of G. Let us practice some questions. This set 5, 15, 25, 35 is a group under multiplication modulo 40. The identity element of this group is
Sorry, 25.
one second. How you have calculated?
Multiplication modular means if identity element is multiplied to it, then the remainder should be the same. So if I've taken by options, so if I've taken 5, first option, 5 into 5 is 25. Then remainder will not be 5. So then 15, 5 is 75. Remainder will not be 5 again. In case of 25, remainder is 5. For all options, the same remainder we are getting.
So 5 into this should be 5. Yes. 5 into 25, 125 and modulo 40, 5. And if it is 15, then also it will be satisfied. Yes, answer is 25. Consider the quotient group Q by Z of the additive group of rational numbers the order of the element 2 upon 3 plus Z in Q upon Z is
इसको कैसे अप्रोच करेंगे? क्योंकि क्यू बाई जेड तो रैशनल नंबर हो गए ना, जिसमें हमारे होल नंबर्स नहीं आएंगे. मतलब पी बाई क्यू बाई क्यू इज नॉट इक्वल टू 0 and 1.
क्वेश्चन ग्रुप Q upon Z, जो कोसेट्स वगैरह पढ़ते थे. Q upon
अच्छा.
Z आपका कैसा दिखेगा? P plus Z, P belongs to rational, and I need to find the order of this element. What is the definition of order of an element?
That is, we apply the operation up to n times such that it becomes identity, no?
In case of quotient group, identity is the group present in the denominator. So here identity is Z. So 2.3 plus Z plus 2.3 plus Z. So I will get 4/3 plus Z. Again 4/3 plus Z plus 2/3 plus Z. So it will be 6/3. 2 plus Z. So as 2 is a integer, so it will get absorbed in this integer only. So I am getting Z. So I have added 2/3 plus Z 3 times. Then I am getting this as identity. So order of 2/3 plus Z will be 3. Is this clear? Clear?
So in this case, the identity lies in denominator part, right?
Yes.
Now it is clear.
ठीक है. Let H denote the group of all 2 cross 2 invertible matrices over Z5 under usual matrix multiplication then the order of the matrix two, three, one, two in H is
case 1 2 आया ना ऑर्डर,
इसका
2 आया हो।
नहीं,
ये ऑपरेशन हुआ, तो ही आ रहा है।
if this is matrix A,
हाँ
then I need to multiply A matrix until I get identity. What will be the
यस,
identity?
2 फर्स्ट 2 में ही आ गया ये तो। पहले हम इसको मल्टीप्लाई करेंगे तो आएगा 7 12 4 7, तो ओवर Z5 में मैंने चेंज कर दी एंट्रीज। दिस इज इक्वल टू 7 4 12 7, तो ओवर Z5 it becomes 2 2 4 2 2 4 2, then again multiplying 1 2। अच्छा, मैंने पहले इसको लिया है 2 2 4 2 को, फिर 2 3 1 2 को मल्टीप्लाई किया, तो फर्क पड़ेगा?
आपका आया डिफरेंस?
मैंने हाँ, इसके बाद आया 6 10, मल्टीप्लाई करने के बाद 6 10 10 16। नहीं, इसमें क्या आएगा वो मैं चेक कर लेती हूँ, पर मैंने पहले 2 2 4 2 लिया है, फिर 2 3 1 2 लिया।
नहीं, हमेशा ऐसे लिया करो 2 3 1 2। पहले जो भी मैट्रिक्स हमें गिवन है, ए क्यूब को लिखना है तो ए इंटू ए स्क्वायर, इस तरीके से।
अच्छा, इससे फर्क पड़ेगा, चेक करती हूँ।
बिकॉज ये मैट्रिसेस एडिशन के केस में तो कॉम्यूटेटिव आते हैं, बीलियन आते हैं। मैट्रिक्स मल्टीप्लिकेशन के केस में कॉम्यूटेटिव प्रॉपर्टी होल्ड नहीं करती।
अच्छा, नहीं फिर भी आइडेंटिटी बन रही है, 16 10 10 6
16 10
10 10 6,
हम्म
और फिर ये 1 0 0 1 बन गई फिर से।
तो ऑर्डर विल बी 3।
तो 2 नहीं हुआ?
क्यों 3 हुआ ना? ए क्यूब ए टू द पावर n इज इक्वल्स टू आइडेंटिटी, तो जो n होता है वही तो आपकी ऑर्डर बनता है।
हाँ, तो हमने इसको, अच्छा
ए स्क्वायर ए क्यूब हुआ ना।
ठीक है, ऑर्डर 3 आई।
Now try this.
B and C, and
What about A?
A में डिटर्मिनेंट जनरलाइज लीनियर ग्रुप का है तो 1 होना चाहिए, तो L को 0 लेंगे फिर.
सिंपल जो
नहीं सर, डिटर्मिनेंट नॉट इक्वल टू 0 होगा, नॉट 1. तो बी ये भी, हाँ फिर ए भी आएगा मेरे हिसाब से. तो
ऑल ऑप्शंस
तो
आर
कि अगर हम एक आइडेंटिटी मैट्रिक्स भी ले लें तो भी आएगा ये.
So GL3C, this is equal to 3x3 matrix. Entries are from complex numbers such that A is invertible, means determinant of A is non-zero. A part H is equals to A belongs to M3 C such that determinant of A is equals to 2 to the power L. L belongs to complex numbers. So let A comma B belongs to H. Here I am applying one step test. So determinant of A is 2 to the power M1. Determinant of B is 2 to the power M2. M1 and M2 are integers. Determinant of B inverse, this will be 2 to the power minus M2. Therefore, determinant of AB inverse, this is determinant of A into determinant of B inverse. So 2 to the power M, where M is integer. So H is subgroup of GL3C. It should be L belongs to integers only. बिकॉज हमने कभी भी ऐसा कोई डिटर्मिनेंट नहीं देखा कि 2 टू द पावर आयोटा करके हमारा कोई डिटर्मिनेंट आए. कभी नहीं आता ऐसे डिटर्मिनेंट हमारा, चाहे एंट्रीज कॉम्प्लेक्स ही क्यों ना हो. बी पार्ट H is equals to 1 0 0 alpha 1 0 beta gamma 1. Alpha beta gamma are complex numbers. Let A is equals to 1 0 0 alpha 1 1 0 beta 1 gamma 1 1. Matrix B is equals to 1 0 0 alpha 2 1 0 beta 2 gamma 2 1. So B inverse will be 1 A 1 2 0, and after that it's transpose also, so it will come here, and it's alpha 2 1 0 alpha 2 gamma 2 minus beta 2 minus gamma 2 1. AB inverse will be, on multiplying these two matrices I will get 1 0 0 alpha 1 0 beta gamma and 1. Alpha beta gamma belongs to complex numbers. AB inverse belongs to H. So H is a subgroup of GL3C. Similarly, we can verify C part also. So answers are options A, B, C. Now next is cyclic subgroup of G generated by an element of group G. Let G be a group and A belongs to G. Then the cyclic subgroup of G generated by A denoted by this is the set A to the power n such that n belongs to integers, and this A is called the generator of this group G. This generator is always an abelian group. Abelian subgroup of G. If order of element is m, then order of generator is also m. Also, generator A is equals to A inverse, means generator A is equals to generator A inverse. Next is intersection of two subgroups. Let H and K be two subgroups of a group G. Then if H and K are two subgroups of group G, then their intersection is also a subgroup of G. H intersection K is also a subgroup of G. Note, union of two subgroups need not be a subgroup. For example, let G is equals to set of integers, H is equals to 2z, K is equals to 3z. 2z means 0 plus minus 2 plus minus 4 plus minus 6 and so on. 3z means 0 plus minus 3 plus minus 6 plus minus 9 and so on. So H union K will be now 2 belongs to H union K, 3 belongs to H union K, but 2 plus 3, 5 does not belongs to H union K, means closure property fails. Therefore H union K is not a subgroup of G. Now when we can say that union of two subgroups is a subgroup if H and K are subgroups of a group G, then H union K is a subgroup of G if and only if Either H is contained in K or K is contained in H. Second, let H and K be subgroups of a group G define HK. H belongs to H, K belongs to K. In general, HK is not a subgroup of G. HK is a subgroup of G if and only if HK is equals to KH. Order of HK is equals to order of H into order of K divided by order of H intersection K. This formula is important. One question on this formula only. Let G be a group and let H and K be two subgroups of G. If both H and K have 12 elements, which of the following numbers cannot be the cardinality of the set HK is equals to HK such that H belongs to capital H, K belongs to capital K.
D60.
Yes. It is given that order of H is 12, order of K is 12, and formula is order of HK is equals to order of H, order of K, upon order of H intersection K. So order of H intersection K will be 12 into 12 upon order of HK. So A part. Now by options I can put order of HK 144 upon 72. This will be 2. This is possible. B part, order of H intersection K is 144 upon 60. This is not possible. So answer is option B. Next, let G is equals to set of integers and M and N are elements of Z. Then the smallest subgroup of Z containing M and N is GCD of M, N. Now some important results. Let G be a group. First, if A and B belongs to G, then order of AB is equals to order of BA. Should I discuss its proof also or should I skip it?
Skip the proof.
ठीक है. Next, conjugation. Let G be a group and A belongs to G. Then the conjugacy class of a class of A is denoted by class of A. This is equal to XA X inverse such that X belongs to G. So class of A is a subgroup of G and order of XA X inverse is equals to order of A. Next, let G be a group and A belongs to G be such that A is the only element of order 2 in G. Then A belongs to ZG. Means if I have any group and in that group only there is one element which has order 2, then that element belongs to center of group G. Next, let A, B belongs to G such that order of A is equals to M and order of B is equals to N and G is abelian. Then there exists C belongs to group G such that order of C is equals to LCM of M, N. A and B are two elements of group G such that order of A is equals to M, order of B is equals to N, G is abelian. Then there exists an element from group G such that order of that element will be LCM of M and N. if x, y and z are elements of a group such that x, y, z is equals to 1, then
ये एक्स वाई जेड इक्वल टू 1 जो है ये ऑर्डर है या मल्टीप्लाई है, क्या है? ऑर्डर ऑफ एक्स वाई जेड 1 है, क्या है?
नहीं, ऑर्डर नहीं, बस वैसे ही गिवन है कि 3 एलिमेंट्स हैं किसी ग्रुप के, उनका मल्टीप्लिकेशन 1 है।
अच्छा ठीक है, तो इसमें ग्रुप है ना, तो एसोसिएटिव प्रॉपर्टी होल्ड करेगी ना, तो 1 और 3।
यस, एक्स वाई जेड इज इक्वल्स टू 1. So I can pre-multiply by x inverse, then x inverse x by z is equals to x inverse. It will be by z equal to x inverse. Then I can post multiply by x, by zx equal to 1, and similarly I can show that zxy is equals to 1. So answer is options first and third. Next concept, cyclic groups. A group G is said to be cyclic if there is an element A belongs to G, such that G is equals to A to the power n, such that n belongs to natural numbers. Means all the elements of the group can be generated by this A. A belongs to G is called the generator of G. G is equals to generator A. Cyclic groups are abelian. Means cyclic implies abelian. Alternate definition of finite cyclic groups. Let G be a finite group of order G is a finite group of order n. There exists A belongs to G such that order of A is equals to n. Then G is equals to generator A. Next, if A belongs to G is a generator of G, then A inverse belongs to G is also a generator of G. An infinite cyclic group has two generators, A and A inverse. For example, first, Z under usual addition is a cyclic group one and minus one are the generators. What does this mean? That I need to generate all the elements of group G. Operation is addition. So here A to the power n will mean that A plus A, so on, n times. So if I use 1, then I can generate all the positive integers, and by using minus 1 I can generate all the negative integers, and by using both of them 1 plus minus 1, 0 will be generated. So all the elements of this Z will be generated by using these two elements. So whenever we have an infinite cyclic group, then it has only two generators, A and A inverse. Here A is 1, and in case of addition operation A inverse is minus 1. Is this clear?
Yes, ma'am.
Next, for each n belongs to natural numbers, Zn is a cyclic group under addition modulo n. A belongs to Zn is a generator if and only if GCD of A comma n is equals to 1. Next, U8. Tell me the elements of U8.
नहीं पता इसके बारे में.
U8 में वो सारे एलिमेंट्स आएंगे जिनका GCD इस 8 के साथ बना है. So 1, 3, 5, 7. Now order of 1 is, and this group is under multiplication. ये कल मैंने बताया था ना ग्रुप ऑफ यूनिट्स, मुझे लग रहा है मैंने बताया था. ये रहा multiplication modulo n. So this is the under multiplication modulo 8. So their identity is 1. So order of 1 is 1. What will be the order of 3? थ्री का ऑर्डर निकालना है तो 3 की पावर 1. नहीं 1 नहीं आएगा. मैंने एक ऑर्डर के टाइम ये भी बताया था, सिर्फ और सिर्फ आइडेंटिटी एलिमेंट का ऑर्डर बनाता है. 2 आएगा. 9 मॉडलो 8 1.
3 के पावर
5 का
2.
यस
7 का भी 2 आएगा.
yes. So order of U8 is 4 because it has 4 elements. Now there does not exist any A belongs to U8 such that order of A is equals to 4. So if I want that this U8 is cyclic, then I should get at least one element from this U8 whose order is same as the order of the group. Means order of group should be same as order of A. Then only I will say that G is cyclic. Okay. So there does not exist any element whose order is 4. So U8 is not cyclic. Note, U8 is an abelian group which is not cyclic. Therefore, every abelian group need not be cyclic. Means cyclic implies abelian, but converse need not be true. Counter example is this example only, U8. U8 is abelian. Is this clear?
Yes.
Next, Let G be a group and A belongs to G. If A has infinite order, then all the distinct powers of A are distinct group elements. Means A to the power minus 3, A to the power minus 2, A to the power minus 1, identity A square, A cube, and so on. These are all distinct elements. Second, if order of A is equals to n, then generator A will contain n elements only. Generator A order is same as order of A. So it will have identity A square, A cube, so on till A to the power n minus 1. If A to the power A is equals to A to the power j, then n divides I minus j. If A to the power k is identity, then n divides k. A to the power k is identity, then order of group divides k. Generators of cyclic groups. Let G be a cyclic group of order n such that A belongs to G is the generator of G. Then G is equals to generator A to the power k if and only if GCD of k comma n is 1. So G is a cyclic group of order n such that A belongs to G is a generator of G. Then G is equals to generator A to the power k. This is possible only if GCD of k and n is 1. Next, fundamental theorem of cyclic groups. This is important. Every subgroup of a cyclic group is cyclic. Means if a group is cyclic, then its subgroup is also cyclic. If order of A is equals to n, then for each positive divisor k of n, there is exactly one subgroup of order k generated by A to the power n by k. If order of A is n, then for each positive divisor k of n, there is exactly one subgroup of order k generated by A to the power n by k. So after this, we will discuss in the next class.